We'll now turn our attention to getting another partition function, this time for the rotational motion. So this will be the rotational partition function. And to recall a little bit, you've covered previously the quantum mechanical problem of a rigid rotator model for a diatomic molecule. And here I've got two different molecules, A and B, separated by a bond length of a little r, we'll call it. And just to recall, uh, if A and B are the same kind of atom, so they're both oxygen, for instance, then we have what would be called a homoatomic molecule, the same. If A and B are different, maybe CO, carbon and oxygen, then we have what's called a heteroatomic molecule. They're both diatomic molecules, but one has the same atoms and one has different atoms that comprise the molecule. Some people call these homonucleic molecules and heteronucleic. So don't be surprised if you hear those terms as well. I've heard them on occasion anyway. Well, you found previously that the quantum mechanics for the rigid rotator gives this expression for the energy of the rotator. It's actually the energy levels are depend on the quantum number J, which is the rotational quantum number. And depends on, I like it in this form, h bar squared over 2I. Remember, J goes from 0, 1, 2, etc. And there's a degeneracy of each one of these energy levels that goes like 2J plus 1. So when J is 0, the degeneracy is 1. When J is 1, the degeneracy is 3, and so on. In the above, just to set my notation, I'm not real familiar with the notation necessarily that you guys have used, so I just wasn't there in previous lectures. But I use h bar to be h over 2 pi, so I'll use that symbol. I remember the rotational inertia is the reduced mass for these diatomic molecules times the bond length squared. Okay? And the reduced mass is the mass of A times the mass of B times the mass of A plus divided by the mass of A times the plus the mass of B. Can't talk this morning. J is called generally the rotation or the rotational quantum number. And our task in this video is to get the rotational partition function. This would be on a molecular level, so your book would write this as small j. Some books would write it as a small z. I've been writing it as z sub 1 for molecular level, but this was just for a single rotator system at this point. And that is just the sum over of these exponential Boltzmann factors, where E is the energy of, you can sum it over states, or in this case, it'll be easier to sum over the energy levels, in which we've got the rigid rotator energy divided by kBt and the respective degeneracy of each one of these J levels. Just to, again, set our notation a little bit, remember Z in general is Z1 to the nth over n factorial for a system that has capital N particles, and this relates to the translational, rotational, vibrational, and maybe even others, electronic, even nuclear. But in our case, it's Z to the n. A rotation is the one that we're focusing on, although I'm going to drop the 1 here. Again, your book would call these little z's, probably small z's. Some people would call them small q's. I've seen that notation used quite a bit, so don't be surprised if you see that. So plugging in to this expression here, what we know about the rigid rotator from the quantum mechanics. Our energies are given here. and the degeneracies of the 2j plus 1, and we have to sum it over all energy levels, in this case from 0 to infinity. It's convenient. It's not absolutely necessary to do, but lots and lots of people do it. And that is, this is getting kind of jumbled up here, so we just lump some parameters together that ultimately has units of temperature. So this is the rotational temperature, theta, I'll call it rot. And if you look at that, I'm just peeling off everything from this expression, h bar squared 2I kb, everything that is not a j and is not the temperature. So often I'll use it in this form. Sometimes I'll write out what h bar is, and so you get a slightly different expression. I think I'd maybe do that later on. A lot of times people will write it in this form as well. Is they'll pull out a factor h and then define this quantity b for h b over kb, and that's the Boltzmann's constant. So that's pretty common as well. In this case, this factor of b has units of what is it? It has to have units of reciprocal seconds. H has units of joule seconds, and so if b has units of seconds inverse, then this top has units of energy, and kb has energy per Kelvin, and so the energies will cancel out, and this all comes out to be in Kelvin. Here, b in terms of this notation is just these factors here. So you have to be a little bit careful. Some books will use a slightly different terminology for b. They won't have this factor of h in it. Okay? But then, to me, the units aren't quite as clear. Okay? So with that introduction of the rotational temperature of this rigid rotator, theta ROT. Incidentally, this should be a capital theta. So if you're writing things, make that however you write your capital theta. Our partition function now becomes 2j plus 1 e to the minus theta rotation over t. So notice the j's are just numbers, and so this is all dimensionless up here. Well, it takes some experimentation, but let me just give you the results of a body of experiments that have been done over the years, and that is that so long as this ratio, the theta rotation divided by the temperature you're at, is small, and that's is generally true for normal sort of room temperature-ish temperatures, and for diatomic molecules, so long as the molecules don't have one of the atoms or both of the atoms being hydrogen. It doesn't. Once you get into hydrogen, you have to do some additional gyrations, mainly because of they're so light. So it's a small mass. But it's so long as we have those conditions. So, for instance, O2. Oxygen is a good approximation around room temperature type conditions, or even fairly high above that. But in that event, we can do like we've done before for these conditions, and we have the sum, and since this is a very, very small number, then basically we can turn this sum, discrete sum, into a continuous sum or an integral. So to a good approximation, this exact value is approximated by this under these conditions of more or less normal temperature ranges, really even up to well beyond room temperature. And we get this, but now dj we have to integrate over it. And I did that real quickly. I just did a change of variable, so I let x equal j plus 1. And remember, j plus 1 is j squared plus j. And I take the differential of both sides of this. Dx then is equal to 2j plus 1 gj. And if you notice, that's exactly what's here, which works out nice. So 2j plus 1 dj is just dx. And then what's up here, of course, is just x. And so I can rewrite this as an integral from x equals 0 to x equal to infinity. When j is 0, x is 0. And when j is infinite, x is infinite. And that gets it into something that's maybe a little bit more tractable in terms of just writing everything out. In any event, you can integrate this exponential. It's simply the exponential here again. And then you have to divide by the factor in front of it, which flips things over instead of theta rotation. It's t over theta rotation with a minus sign. And then evaluating that at the upper limit and subtracting at the lower limit. The upper limit is e to the minus infinity, and so this term goes totally out. And we're left with just this term, evaluated at the lower limit, which is 0, but e to the 0 is just 1. Minus minus is a plus, and so we get 0 plus t over theta rotation. And we get the rotational partition function is just the absolute temperature divided by that rotational temperature, characteristic temperature. That argument works fine for the heteroatomic molecules. CO, for instance, carbon monoxide. It doesn't work well for homoatomic molecules like O2. And the way you correct for it, and the reason it doesn't work for those is because of some symmetry arguments. If we have enough time, I will go into it. But for us, one introduces simply what's called a symmetry number, and in here, and the symmetry number accounts for overcounting in highly symmetric molecules the number of states, basically. For us, and for diatomic molecules, and for linear molecules that are heteroatomic, one has that the symmetry number sigma that I've introduced here is 1. And for homoatomic molecules, these would be for diatomic molecules, would have a molecule of type A here, or an atom of type A and of type B here that are different. And if they're the same, then the symmetry factor becomes 2 for if I have AA, so like O2 if this was oxygen and oxygen. So the rotational partition function is really very, very simple formula. And we'll look at some implications of that on the next